All right, part two, chapter two of our chemistry book is we're going to look at the periodic table. And when you're doing chemistry, honestly, the periodic table is your best friend. So we're going to talk about the parts of the periodic table, and we're going to talk about what it represents and some of the things that you'll find on the periodic table. One of the first things, of course, is we're going to find the symbols for the elements. When you look at an element, you've got, and the symbols vary. You've got either one or two. One thing to remember about the symbols is the first one's capitalized, and if there's a second one, it's small. Okay, there's not very many with just one symbol. Kind of the main elements that have been around or that were discovered first have just one, but most of them have two. The other thing you'll see if you see it written like this, on the top you have what they call the mass number. That's how much the atom weighs. And again, this is an AMU, or it's the number of protons and the number of neutrons added together. Okay, because a proton, every proton that an element has a unit of 1 for its mass, and every neutron has a unit of 1. So if you want to know the total mass, you add those together. And then the atomic number is the number of protons. Okay, that number never changes. We're going to talk about isotopes today, and we can change the number of neutrons, but we never ever change this number, the atomic number, because if you change the atomic number, you change the number of protons, you change the element. Okay, but when you're looking, this is how they write it out a lot. You'll have a number on top, that's the mass. You'll have a number on the bottom, that's the number of protons, or what they call the atomic number, and then your symbol. Okay, elements are represented again by one or two, mostly by two. And again, the first one's always capitalized and the second one's always small. We do this so we can write out equations and we don't have to write out the big long words. Okay, all atoms of the same element have the same number of protons. So all atoms of carbon have 6 protons. If you change that number, then it's not carbon anymore. Okay, so that's the atomic number. That's the number on the bottom. And I'll show you where that's on a periodic table here in a little bit too. And then again, the mass number is what it weighs. And each proton has been assigned a mass of 1 AMU. Each neutron has been assigned a mass of 1 AMU. So when you add them together, you get the total. Okay, so that's how you figure out protons and neutrons. Now, if you want to figure out electrons, it's really simple because an atom doesn't have a charge. So if you have 6 protons, you also have 6 electrons, because 6 positive charges, you have to have 6 negative charges. Okay, now what I was saying before, the proton number never changes, but the neutron number can. So they have something called isotopes. And what an isotope is the same number of protons, but different number of neutrons. Remember, neutron doesn't have a charge, so what it does is it either makes it heavier or lighter. It's kind of us like before the holidays and after the holidays, those, yeah, you know what I'm talking about. Anyway, here's an example down here of carbon. Carbon has 4 isotopes. It has carbon 11. Now the protons, you notice, is always the same. And the electrons are always the same in this case, because this is an atom. Later on, when we talk about ions, the number of electrons can change. But for right now, when we're talking about atoms, they're the same. So the number of neutrons, okay, if it's carbon 11, if I take 11 minus 6, I get 5. That's the number of neutrons in carbon 11. Carbon 12, which is the most common form of carbon, I take this, because this is both the protons and neutrons. If I subtract the protons, I get the neutrons. So the same, 6 and 6. Carbon 13, again, 6 proteins, 13 minus 6 is 7. And for carbon 14, we take 14 minus 6 and we get 8. So they have different number of neutrons. So carbon has 4 isotopes. All the elements have at least 2. Okay, so when you're trying to figure out the mass, you have to calculate all the isotopes in there. And that's why when you're looking at the mass of an element, it's not just a whole number, because if a proton is 1 and a neutron is 1, when you add them together, it should be a whole number. But we have to take in account the relative amount of each isotope, and that's why they're not whole numbers. And you can see here almost 99% of carbon is, excuse me, is carbon 12. Okay. All right, the atomic weight, because they're just too small to, measure on like you can't throw an atom on a scale, they're too small. So that's why they came up with this relative amount, and they use average masses in the calculations. Okay, And again, when we do an average mass, when we have the atomic weight that's listed on the periodic table, we use all the isotopes for that element. Some elements have 7 isotopes, some have 2, but all of them have a couple isotopes, okay? And so that's how we figure out their atomic weight. And the way we do it, and the next slide, I'll have an actual slide to show you, but you take the mass of the isotope times its abundance. And it says fractional natural abundance. The thing you got to remember is when you get a percent, like if you get 95%, well, that's 0.95. You got to remember to change it back into a decimal. And then you add them all together. And again, this probably explains it better. I'll show you a problem. Okay, so we have sulfur. Sulfur has 3 isotopes. 95% of all sulfur atoms have a mass of 32. 0.76, so less than 1%, have a mass of 33. And 4.22% have a mass of 34. So there's your 3 isotopes of sulfur, 32, 33, and 34. Sulfur has 16 is its atomic number. That means it has 16 protons. That never changes. Okay, so if I want to figure out the mass, this is what I'm going to do. I'm going to take my 95% and I'm going to change it to 0.95. I'm going to move that decimal over 2 because percentage, remember, we multiply by 100 to get it there. And then I multiply this mass that it gives me. Now, sometimes it'll give you masses like 31.999675. You know, those are more specific, but this works as well. You just got to take the mass they give you. Here, for this one, I can't use 0.76. I have to 0.0076. Again, remember, I got to move that decimal over 2. So, and then I multiply by 33, and I get 0.25. And then the last one, I take this number, and I make it 0.0422 times 34. And again, that's its mass. So I have these 3 numbers, I add them together, and I get 32.08. That's AMU, atomic mass units. So if you look at a periodic table, and I put that down, you'll see, you can check. Look underneath sulfur, look for its mass, and I think it's 32.084 or something like that. So it's really close. It's a way to double check to make sure you did it right. Okay? So again, you take your numbers and you take the percentage, but change it back to a decimal, multiply by the number it gives you, the mass it gives you, and then just add them together. And that gives you the mass, the relative mass of your element, and that includes all the isotopes. Okay, here's my periodic table. You can't see it very well, but it says 32.085, I think it says. So that's one way you can always check to make sure that you've done it right. If your number should be close to this number under here. Okay. All right, so we're going to talk about the periodic table. The periodic table is a way of organizing the elements. Okay, the first guy that did it was Dmitry Mendeleev, a Russian guy. He's the one that he put elements on cards and he organized them according to their characteristics. There were some other guys that worked on it as well, had the same ideas, but Mendeleev published first, so he gets the credit. Anyway, you take the elements and you arrange them in order of atomic number. See, this is the atomic number on the top. 1, 2, 3, 4, 5, 6, 7, 8. They go in order. When Mendeleev first did his table, he did it by atomic mass. And while it kind of worked, there's a few spots. I don't have the masses on here, but like Trillium weighs more than iodine, and there's a couple spots in here where it doesn't work. So his table was good, but it wasn't great. It had some issues. So he had to fix it. He didn't fix it. Another guy came along by the name of Meyer, and he fixed his table. So all the elements are put in the table by the number of protons that they have, by their atomic number. Okay? Okay? And the reason why, when you write out the symbol, you write the symbol and you write the mass on top and you write the atomic number on the bottom. On the periodic table, it's opposite. They have the atomic number on top, the symbol, and on this one, they don't have the mass because it's pretty tiny, but the mass would be underneath. Okay? So the weight of the element appears, and it's not on this version, but on the one I just showed you, it is. Okay? When you look at a periodic table, if you go across, okay, there's 7 rows. These 2 rows right here actually fit in here. You can see it goes 56, then 57, and then after 70 it goes back to 71. The reason they put them down here, first of all, this table would be super, super long and it would be hard to put on one piece of paper. And second of all, these guys all have similar characteristics. These are Most of these are man-made elements that were discovered in a lab. Okay, so these guys go down here and then you go back up. But there's 7 rows. Those are called periods. When you go up and down the columns, these are called groups. And there's 18 of them. And when you're in a group, you're similar to the guys above and below you. When you're in a period, not so much. Okay, they don't necessarily share similar characteristics. But when you go up and down a row, these guys have similar characteristics, these guys do, and so on. Okay, and if you're in a group, again, they have similar chemical properties, and the reason for that is because they react with the same things because of their electrons and the outer energy, and we'll talk more about that later. Okay, the other thing about it, the reason why it's called the periodic table, periodic means repeating. Okay, so like the days of the week, every 7 days you know it's going to be Monday again. Well, the days of the weeks are periodic. They repeat after every 7 days. Well, the periodic table does that. After every so many elements, it can be 8 and so on. But each row or each column, excuse me, you end up getting characteristics that are similar to each other. So they call that, that's where the periodic came. They start to repeat patterns after so many. Okay, when one looks at the chemical properties of elements, they have a repeating pattern. Okay, so if you look at helium, below helium on the periodic table is neon. Well, non-reactive gas, non-reactive gas. Below neon on the periodic table is argon, non-reactive gas. Lithium is a soft reactive metal. Well, below lithium is sodium, soft reactive metal. Below sodium is potassium, soft reactive metal. So they start to have characteristics that repeat themselves. That's where the word periodic came from. Okay, we have some groups that have similar names. The 5 groups, we have the alkali metals, the alkali earth metals. This is the oxygen group, okay? Chalcogens or the halogens and the noble gases. And actually, what I'm going to do is I'm going to go back to the periodic table here and show you where they're at. Sorry about that. Okay, here we go. So these guys, not including hydrogen, are the alkali metals, okay? These are the most reactive metals, and they react with the same things. These guys are the alkali earth metals. These guys are your oxygen family, the chalcogens, and these are the halogens. Halogen means salt former, and these guys are the noble gases. So those are the groups that have names. Now I got to get back to where it was. Sorry about that, you guys. Okay, so the metals, which most of your elements are metals. Don't count hydrogen. Hydrogen is an element among itself, but all of these yellows, those are all metals. So you can see almost 90% of the elements are metals, and they're found over here, and they have certain characteristics. They're shiny, which means they have luster. They conduct heat and electricity, which is what we really love metals for. And most of them are solids except for mercury. Mercury is the only metal that's a liquid at room temperature. Okay. Then we have our non-metals. These are the green guys over here. And hydrogen. Hydrogen hangs out with the metals. Hydrogen, like I said, is a crazy element. But these guys have every characteristic that metals don't have. Okay, they're not shiny. There's some solids, there's some liquids, there's some gases. They are not good conductors. They're actually called insulators. They're not shiny. You can't hammer them to sheets. You can't stretch them into metals. Everything that a metal is, a non-metal isn't. Okay. And then we have what they call the metalloids. And the cool thing about the metalloids is they're in between the metals and the non-metals. And they have properties of metals and non-metals. You got these, and there's only 6 of them. Okay. These guys are semiconductors. These are the reasons why we get to have online classes. Semiconductors are what are used in computers and cell phones and video games. They make it so that information can be sent through, but if it's a conductor, it goes too fast. If it's a semiconductor, it goes through slow enough so a processor can read it. So metalloids are the reasons why we have all our cool toys, especially silicon and germanium. Those are the 2 ones. Okay, so all elements are either metals, non-metals, or metalloids. Most are metals. You got your non-metals over here, and then the metalloids are in between. And I'm going to run out of time here, so that's where I'm going to quit. When we meet again, we're going to start talking about naming compounds. I hope you enjoyed part 2.